And let me just start saying that, you know, how disappointed I am actually that I cannot be there today. In a way, you know, as you actually detailed, really the cab did take the wrong turn and didn't take me to the airport in time. But let's also celebrate the power of networks, which is the fact that we can still be together to the degree that I can give my talk and I can, in this imperfect way, I can still be present at your meeting. And my goal today is really to tell you a bit about networks, and I have 45 minutes to do so. Am I correct?
30.
30. I'm glad we asked. And so what I'm going to do is turn on my slides now and start talking about really network science in general in the context of complexity. Just to make sure, are you seeing my slides now?
Not yet. You have to start sharing.
All right, so then one more step. Okay, beautiful. And then I say desktop, start screen share, and then we should be good to go. How's that?
Yeah, it's coming up. Start shine. Bravo.
All right. I don't think normally I'm that funny, so there must something happen, but that's okay, let's go on. So today, what my goal is really to tell you a bit about how we think about complexity from the perspective of networks. And the reason we think about networks, or in my lab we think a lot about networks, is because many complex systems, many systems that we perceive as being complex, really have fundamentally a very complicated network structure behind them. What you see here is the map of the internet, which is the basic communication device that we use day to day, through which I'm giving the talk today. And it's showing actually how interconnected network it is, and we'll come back to that and talk about in a second more. But equally complex in our perception is our self. What you see in this map is actually a map of the human cell and how things connect to each other. And of course, you can also think about the complex system being the society, where all of us link to each other through friendship and other associations. And this is illustrated by a map that Facebook put out about 2 years ago, telling us how their consumers link to each other, who is connected to whom. Now, all of these systems, society, the internet, the cell, are truly complex systems, and we study it as such. But the challenge for us is really to understand how much of this complexity is coming from the network, the underlying network that connects its different components. So my first challenge today is to tell you a bit about how do we describe mathematically this particular network. And some of the early work in this direction started with two mathematicians, Paul Erdős and Alfred Rényi, who said, these networks are very complicated. We don't really know how they connect to each other, but from a mathematical perspective, they are very simple, because they are nothing but nodes connecting to each other by links. But they also said that we as mathematicians do not know which nodes are connected to each other, so let's assume that these nodes are connected randomly to each other, which means that you toss a dice and you connect them if you get a 6, or in other words, with a certain probability you connect each pair of nodes. What you see on this plot is really on the left-hand side is a very simple realization of a random network like that. But in reality, of course, what Erdős and Rényi studied are very, very large random networks. And I believe, by the way, as a historical curiosity, is that while both Paul Erdős and Alfred Rényi are Hungarians, they came up with the idea to work in random networks in a visit to Holland while we were both visiting there, and that's where the idea came from. So in a way, you know, even though this was published in Hungary, the ideas are somewhere rooted in somewhere in your land closer to you than to me right now. That being said, the question is, what happens if I have a very, very large network and connect them with a certain probability? And I'm going to try to show this in this coming video. The quality may not be too good, but let me just tell you the basic picture. If the probability of nodes is very small, that p is equal to 0, then you don't have anything connected. As you increase the probability, more and more nodes get linked up. And what Erdős-Rényi has predicted, and there will be a critical probability at which all of these different clusters connect to each other and a network will emerge. So effectively, they said a network doesn't emerge continuously, but for a long time, wide range of connectivity, you do not have a network, and then through a phase transition, you go from a no network to a network state. But that is not what I'm going to care about today. Rather, what I would like to talk about today is one important prediction of the random networks. As we said, in a random network, the nodes are connected randomly to each other. That is, the dice decides who's connected to whom. So some nodes end up somewhat richer, like this node has 4 links. Other nodes are less rich. This has only 1. If you want to characterize that, you look at the degree distribution of the network. The degree of a node is a mathematician's way to say how many links it has. So the node with 4 links has degree 4, with 1 link has degree 1, and the degree distribution of the Erdős-Rényi network follows, as they showed, a Poisson distribution. Now, what is that telling us? What it tells us is that the vast majority of the nodes have approximately the same number of links. Their degree is around the average. But the Poisson is a very fastly decaying function as you get away from the average, and consequently, it means that it's very, very unlikely to have very highly connected nodes or not so connected nodes. That in other terms, effectively the Erdős-Rényi model or the random network model tells us that there are no outliers in random networks. Most nodes have really comparable degrees. That is, if the society were to be a random network, people randomly meet each other and become friends, then in this society, all of us would have equal number of friends, approximately equal number of friends. There would be no very popular individual, and no one would be left behind. Now, the question we need to ask is that, is this a realistic model of real systems? And that's a question I've been asking, and in 1999, we wanted to actually kind of find an example of systems like that. And before I would go there and give you the specific example, let me give you an example through which we can illustrate many different things. So what you see next is a map of an organization where people, this is actually a real organization where people work in 3 different locations. They're the purple people who work in Budapest, and the green and the blue people work in 2 offsites. So it's a small to mid-sized company in Hungary. And you know, the question would be, who is communicating with whom? And the reason I'm going to talk about this particular example is because this is a real company where they turn to us, asking the question helping them to kind of answer a particular question. And the question they had to us is the following. The high-level CEO and the high-level management realize that they have a communication problem within the company. That is, whenever they try to make a decision, the information is not getting to the workers, but somehow it's stuck at the highest level, or often the workers, not only they don't get the news, but often know the opposite of what the management has decided. So the question was, what is really going on? And for us to understand what is really going on, we need to understand where is the information spreading, who is talking to whom, what are the channels of information within the company. Now, if this network were to be random, like Erdős-Rényi envisioned, it would mean that every person would be in contact with a randomly chosen subset of the company. And the question is this so? And I'm going to give you the answer as we move along. Let me kind of step back and tell you how we in my lab actually started to think about these problems. And we wanted to be able to map out real systems like this company or some other systems. And we chose not a company in that case, but rather we chose the World Wide Web. Why did we choose the World Wide Web? Because it's a network whose nodes are documents connected by URLs, and we were able to write a robot, which is a piece of software that was able to go from node to node and connect the links, effectively reading each web page and saying what URLs you can find on that. Now, as a result, we got a little map like the one shown on the bottom, and the question we asked, how does this map look like? We expected it to be a randomish looking network because everybody decides themselves where they're going to connect, and there's lots of randomness in those decisions. Yet, to our great surprise, what we found is what we call today a power law in this context. So what you see here on the right-hand side is the probability that a randomly chosen web page will have exactly k links. So horizontal axis is the number of links, vertical is the probability, and I'm showing the data on a log plot. And the fact that the lines, the dots or the circles line up along more or less a straight line tells me that the probability that the page will have exactly k links goes like k to the minus gamma. Now, what does that mean? Why? This is clearly different from the Poisson distribution we expected for a random network. What is the mean? Let me give you a simple interpretation of the meaning. If nodes were to be randomly connected, a network would look a bit like the highway system of US or Europe, where you have cities connected by highways to each other. This is a relatively uniform network where most cities have 2 or 3 highways. You don't find a city with 500 highways, and you don't find any city that would not have at least one road to connect into the system. So this is not a truly random network, but it would look a bit like a random network in the sense that it's very uniform. In contrast, the network we found on the World Wide Web visually looks much more like the airline system of Europe or US, where you have many, many small airports connected by a few major hubs. Like in Europe, Amsterdam is being one of the biggest hubs within the European map. And this is exactly what this power law is telling us, because the power law tells us that rather than having many, many nodes of comparable degrees, we have many nodes that have very small degree on a small k region, and we have a few very, very highly connected nodes or hubs in the system, because the power law is a very slowly decaying function, and therefore it allows the possibility for highly connected nodes or hubs. These networks today are called scale-free networks, and a scale-free network technically is a network that has a power law degree distribution. If all you're going to remember that it's a scale-free network is a node held together by a few major hubs, may be enough to understand the rest. So what we found here in the case of the World Wide Web is that there are some networks that are dominated by hubs, like the airline system, like the World Wide Web. Now the question, are these the only systems? And it turned out that was not the case. And for example, let's go back to our company, our organization that I showed you earlier. And what you see here now is the internal map of the organization. How do we know this? Well, the reason we know that is because we went ahead and effectively used an online platform to interview every single individual within the company, asking them, whom do they talk to on a regular basis? Where do they get the news about their organizational matters? Where do they delegate the jobs? And where do they get their jobs from? So we ask questions pertaining to the flow of information within the organization, as well as we ask questions pertaining to where power lies within the company locally. And we ended up seeing this map, and you can clearly see that there are a few major hubs that hold the company together. And I want to emphasize, these people are not hubs because they think very highly of themselves. They are hubs because several others have pointed to them as being the source of the information that flows within the company. So you see, we have these hubs in organizations. And let's go back to the map of the internet that I showed you earlier. And you see now that there are a few major hubs that hold the whole network together. And indeed, the internet is known to be a scale-free network, which means that it has this power law degree distribution, and you can see visually the impact of that. Now, let me skip one slide actually very briefly, even though it's a fun slide, but we have only 30 minutes. So let me show you one more example of a network. What you see here are biological networks. Now, on the left-hand side, you see our metabolic network, which is the network of chemical reactions within our cells. On the right-hand side, you see the protein interaction network, where the nodes are the proteins and two proteins are connected if they bind together, that is, they do something together in the cell. And particularly if you look at the right-hand side, you can see the basic features of a scale-free network. That is, there are a few major hubs, one here, one out there, and there are many, many peripheral nodes that these few hubs are holding together. So indeed, what you realize is that, and if you do the math, that is, you make the measurement, it turns out that the networks within the cell is also scale-free. What you see in the map here is the map within yeast, which is a simple organism that biologists like to study a lot in the lab. But in 2005 came out evidence that within each of our human cells, there is a similar network, and that is also scale-free. Whether you look at the metabolic network or the protein interaction network, both of them have the scale-free property. Now, if you think about this, is really amazing, because you must realize that the World Wide Web that I showed you first has a history of about 22 years. The internet may be a history of 50 years, airline network at 50 years. This network, however, the biological network within our cells, has a history of about 4 to 5 billion years. So how is it possible that networks that come from completely different area of complexity describe very different complex systems, yet they converge to the same architecture over 20 years, over 4 billion years? What makes these networks to look alike at the architectural level? And equally important question, why do we not see random networks in this context? What makes them scale-free? And that's the next question that I would like to answer next. And in particular, what I want to talk about is really the question, what's wrong with the random network model? Why are we not seeing the hubs in a random network model? And if we want to pose the question that way, we must realize that the random network model has two hypotheses that are not held out in real networks. The first hypothesis of the model is that we start out with a bunch of nodes, and our role as a modeler is to somehow connect these nodes together. The assumption in there is that while I'm connecting the nodes, I am not changing their number. That is, adding only links and not nodes. In reality, however, in networks, the number of nodes is never fixed, but networks continuously expand by the addition of new nodes. Think of the World Wide Web. 22 years ago, we had only one web page, Tim Berners-Lee's first very famous web page, and now we've got more than 1 trillion. How did we go from 1 to 1 trillion? By adding one node at a time. So networks always grow. They expand by addition of new nodes. So if you want to model how a network came to be, we need to model that growth process. What does that mean? I need to start from a small network, and I need to allow for the possibility that new nodes arrive and connect to the existing nodes. Now, if I do that, I have to answer an important question. How does the new node decide where to connect? And Aldo Cherini told us that it decides randomly. I would argue that's not the case, but rather new nodes prefer to link to highly connected nodes. And again, in the World Wide Web, that's easy to understand. You're much more likely to connect to nodes that you know, but we tend to know highly connected nodes, and therefore we arrive to what we call preferential attachment, which is mathematically telling us that the probability to connect to a node is proportional to how many links it has. And let me illustrate that what happens if you put this growth and preferential attachment together. You see a network that is slowly emerging in which hubs will emerge in the system. And the reason for that is a rich gets richer phenomenon. If a node has many more links than another node, the bigger node will attract more links thanks to preferential attachment and will be turning into a hub, will maintain its status. And if you run this network, you will realize that the network will have a power law degree distribution. That is, it will be a scale-free network. Now, the next question you may ask, okay, we know why these hubs emerge. Why do we have scale-free networks? It's because networks always grow, and most networks seem to have this preferential attachment. The question is, so what? Why do we care about these hubs? And I'm going to give you one example that cuts to the heart of complex systems in general, which cuts to the question of robustness. In the introduction, we heard about the concept of robustness resilience. This is one of the first steps in that direction. What is robustness? Robustness is a system's ability to carry on its basic functions, even when some of their components don't work. And to test it, we can start from a small network and ask ourselves what happens if a couple of nodes are being deleted, that they are being broken. Well, it depends on which node you choose. So let's ask a bigger question. Let's assume that I have a big network and I randomly remove nodes corresponding to failures. What will happen to them? And percolation theory gives us a very precise answer to that question. It tells us that if you have a large random network or a large regular network, if you remove a few nodes, it doesn't matter because the remaining nodes can still connect to each other through the remaining links. However, if you remove more and more nodes, you will reach a critical point at which the network will fall apart. Now, so each network has its critical point, can survive errors under the critical point, but not above that. Well, what happens if we do that not for a random network, but a scale-free network? And that's what I'm showing you here on the video on the left-hand side, where randomly nodes are being removed. And you see that the network is shrinking and it doesn't want to break apart. And indeed, we now have a precise mathematical proof telling us that in a scale-free network, the threshold to destroy the network is 1. What does that mean? It means that the only way you can destroy a scale-free network, that is, you can break it apart, if you remove each of its nodes. There is no finite threshold. So these networks are very robust to random failures, but there's a price you pay for that. What if you don't remove the nodes randomly? What if you go on attack? That is, attack means you remove the biggest node, the next biggest node, and then the next biggest node. And what you see that in no time, the removal of the few hubs will destroy the network into tiny pieces. So let's compare the left and the right side. On the left-hand side, I removed 25 nodes, and the network is still holding together. Very robust to random failures. On the right-hand side, I removed 10 nodes, and it's broken into tiny pieces. This is what we call the Achilles heel of these complex networks. They are very robust to random failures, but they are extremely fragile to attacks. Now, the next question, what I would like to do in the last kind of remaining a few minutes is to switch here and talk a little about what do we do right now and how do we think about, and to do that, I'm going to switch over to a different set of problems, which is the problem of control. So in the last few years in my lab, we started to ask the question, can we ever control complex systems? And of course, control is a very loaded word because, what do we mean by that? Do we want to control a complex system like people, the military controls a drone, for example? Because, like completely running every single step what it does. And of course, control has many meanings. Some of them are not desirable. Myself, I grew up in Eastern Europe, and I know certain aspects of control that I don't wish for anyone, which is what we experienced during communism. So what do we mean by control in the context of complex systems? Let me give a simple example. Let's consider a car. A typical car has about 5,000 components. Yet, when we drive a car, we do not think about 5,000 components. If you are in Europe, having control over 4 components gives you full control over the car, which is the steering wheel, your gas pedal, your brake, and your clutch. And by changing the state of these 4 components, you can make the car to go from anywhere to anywhere. And that's what control theory tells us, is that the system is controllable if by controlling a few components, you can control the full system, like you can make the car to go from anywhere to anywhere. Now, of course, a car is controllable because it was built to be controllable. And I urge you not to buy a car that does not have that property that you can control it from these 4 components. That being said, what if I invert the problem? What if I start out from a wiring diagram of a car that I give it to you and say, could you find on this wiring diagram, what are the 4 points from which you can control a car? And that is not an easy answer to that. And of course, if you know how the car is wired and you know much about cars, you may be able to find that. But you would say, why would I ask that question? And I would say the reason I ask that question is because this is a fundamental question in complex systems. What do I mean by that? Well, if you think about what the biologist is trying to do when it tries to understand the complex cells, it tries to find the genes through which it can actually control it. And by changing the state of the gene, it can change the state of the cell. In the same way, if you are a leader of a new organization, the question you are really facing, how can I make this organization go in a different direction? Which are the nodes through which I can actually control the system, even though you don't want to use the control in this context, you would say, which are the nodes through which I can lead the system to a different direction, this organization in a different direction. And this is the question that we've been trying to address. And in particular, the question we ask, what is the minimum number of nodes through which you can control a system like that? And the answer was provided in a paper that we published about a year and a half ago, in Nature. I went too far here. And what we did in here is that we showed that the controllability problem can be solved to the degree that if you give us a directed network, we can identify who are the control nodes, which are the nodes through which you can actually control a system. And let me illustrate that in this organizational network. So what I'm showing you again, a map of the organizational network, and the nodes that for a second vibrated there, if they did on your screen, I don't know if the resolution is good enough, are those who are not the controller. And I wish it would vibrate a bit more, but I forgot to put it on a loop. But down the line, let me go back again and see if I can make them vibrate. And down the line, what you see in this network is that most nodes are actually not in the control case, but there are a few nodes who are control nodes, and those I'm going to show you in the next slide. The red nodes are what I would call control nodes in this particular context, that through which you can actually go ahead and control the system. So what do we have in this context? What we have is a methodology by which, looking at the directed diagram of the network of who's listening to whom, where the power is flowing in the network, we can identify who are the precise control points in the particular system. Now, this is all, of course, only the beginning of trying to understand control. Since this paper appeared a year and a half ago, now more than 300 papers have appeared in the last 3 years that have been using these tools of controlling networks and asking lots of different questions. But nevertheless, we're still at the beginning of the road. But what I'm trying to show is that you can use very precise mathematical tools to ask questions that seemed unthoughtable before, is that how you control a complex system. And we're applying that with the cell and many other systems as well. Now, given where we are with the time, let me kind of conclude with a few thoughts. One of them having to going back perhaps to the map and perhaps answering the question that you may have in your mind. What was the problem with this organization? That is that why did the CEO and the management feel that they have a communication problem? Well, we can see that there are a few major hubs in the company. So you would think that through them, the news can actually spread. You would also hope, however, that the hubs are those who should be the hubs, which is the leadership. Well, let's see if that's the case. Well, here what I'm doing is I'm putting the different hierarchies on the network. The red nodes here in the middle are the directors and the CEO. And the bad news is that you don't see any hubs among the directors and the CEO. Now, let's go one level down, top management. These are the blue guys here on the left. And unfortunately, we do not see any blue guys as a hub. If we look carefully, what we realize is that the hubs come from the bottom. The biggest hub is really an associate, this guy in the middle, who is in the lowest rank actually within the company. Yet, as I'm illustrating in this slide, he's about 2 links away from everybody within the organization. Now, 2 questions come up. Who is he or she? And what do we do with them? And of course, the answer to the first question is clear. We know who is this person. He is the person who is in charge with health and safety within the company. That is, his job is to go from group to group and talk to everyone. As you can see on this map, he has links to everyone horizontally except the higher management that is up here. So he picks up information here, he passes it over there, he has no credible information from the top down. So we know who is he. The question is, what do we do? Do we fire him? Well, that would be the worst thing you can do. What this map is telling us, of course, is that all you have to do is that there are 2 or 3 people in the organization, him, and then 2 or 3 other individuals. And if you tell them what is going on, then the rest of the company will still know that because they are the source of the information on different parts of the network. So in the introduction, we heard about the importance of having an ecosystem, not only to do theory, but also apply these tools. This is one example how these tools can and they are actually being applied in practice. So let me conclude saying the fact that, kind of stepping back and asking the question, what is network science and how do we think about this problem? And at this stage, I'm going to stop sharing actually the screen. And if I could figure that out, how to do that. Here we are. Did my face come back to you or?
No, we have lost it.
Okay, let's cancel. Here we are. Okay. So the question is, why is the network approach so powerful and, why has it got so much attention in the last few years? And this is a question that not only we scientists are asking, but within the US, your counterpart, the national academies, as well as the US National Science Foundation, other organizations have been asking. And it actually has gone as far that the national academies have published 2 books, 2 reports about network science, asking the question what it is and why is it so important for us. And one of the things they we learned through that process of going through that, finding out what it is that the power of the networks is really coming from the fact that not only that many complex systems have a network structure, but networks help us reveal the fact that systems that apparently have nothing to do with each other, like the cell, like the internet, like the social networks, have common organizing principles. So there is a common intellectual trust behind that because it's really telling us that their organization is really shared between them. It could have been otherwise. It could have been that these networks have nothing to do with each other and the topologies we find are more different than similar to each other, because if you think about it, the nodes and the links cannot be more different from each other. But we find this universality across many complex systems. Now, this universality not only helps us understand how the system come into being and how it behaves, but, and this is crucial, it actually allows us to use the same set of tools across many different systems. That is, allows different disciplines to share their tools. And indeed, now we find that my colleagues at Harvard who work in biological networks and in medicine are using the tools that sociologists have developed, to look at betweenness and to find influential individuals. In the same way, sociologists these days, when they try to analyze social networks, use tools and algorithms that computer scientists have developed
to look at the internet, map out the World Wide Web and understand its properties. So it's not only that at the intellectual level we see commonalities between different types of networks, but these commonalities, this universality, is giving us tools that can be shared across disciplines. And that similarity, that universality has been the key to why the network perspective has been so successful. I'm not here to tell you that complexity equals networks. That is not the case. Complex systems have many layers of information on them, like their dynamics, that cannot be captured only based on the network. What I'm here to tell you, that there is no complex system you will understand if you do not map out first the network that connects the components, and you do not understand the structure and organization of this network. So I would say, if we want to understand of any complex system, the network, which is the architecture, is the first step. And then once you got a good understanding of that, you can go to more complex features like behavior, like dynamics, and so on. This is a good moment for me to stop. Thank you very much for your attention, and I'm happy to take any questions you may have or engage in a discussion as you wish.
Thank you very much.